Hi, I'm MadHat, and this is Unspecific. So a while back, I made a video that was called Introduction to Information Security, and kind of went over different ideas about how people can get into information security and different aspects of information security. Since then, I've been meaning to do a lot more videos. Haven't done it yet. So the other day, someone was talking about the OSI model on Twitter, and that this is something good to know for information security, but it was just the infographic of the OSI model. So it really didn't tell much, or why it mattered, or what it means, or anything like that. If you're looking at it and you're looking at, oh, look, layers 1 through 7, what does that mean? So I'm going to attempt to explain the OSI model for those of you not familiar with it, as well as describe why these things matter and how it relates to information security, or at least why it's good if you're wanting to get into information security to know these particular things. So first off, there are 7 layers. Basically, these 7 layers stack together to be able to allow communication across the internet. It's basically how networking works today, and understanding it can help you understand, one, how to look for anomalies, how to look for things that maybe aren't supposed to be happening, but also whenever you are looking for things, understand better what you're looking at. Whether you're trying to develop an application, troubleshoot an application, looking for strange behavior, doing forensics analysis, knowing how the layers work and how they interact can help you a lot. We're going to start off with the first layer, which is the physical layer. The physical layer is no longer really only physical. It takes into consideration things like Bluetooth and 802.11. But for instance, on 802.11, it's the radio component. So we're not talking about being able to log in. We're not talking about being able to do anything other than receive and send back to the signal itself, the radio part. On the physical side, whenever you are connecting a device, it is the RJ45, the Cat5, the Cat6, whatever you are plugging in. It's the full duplex. It's literally the cables running between the network devices and the end devices, and that's really the big part of it. We're really talking about those physical connections, or in the sense of Bluetooth or 802.11, we're talking about the radio connections, not the data behind it. The data behind it comes at layer 2. Layer 2 is the data link layer. The data link layer is where we start getting into things like ARP, and it's a point-to-point protocol. So the way networking works is whenever you start getting into layer 3, which is where you end up with IP, ICMP, and an IP address. If you are looking for the path to a particular IP address, you have to have at least the first 3 layers. The third layer also will help with routing, but basically the way it works is once there's a physical connection, you make a request saying, hey, I need to make it to this particular IP address. And the first thing a computer will do is look at its routing table, its internal routing table, to say what is the next hop, or which direction should I go to be able to get to that particular IP address. If you're not on the same network as the default gateway or your next hop, your computer will say, hey, does anybody know how I get here? And that would be a lookup in the routing table. So somebody will respond and say, yes, you need to go here first, which will be an IP address on your subnet. If you'll notice, an IP address is comprised of 2 parts, an IP address and a subnet mask. The subnet mask basically says how many machines, or how many IP spaces or addressable spaces there are within that network range. And it also identifies the broadcast IP address, which is where ARP normally happens. ARP is Address Resolution Protocol. And what it does is whenever you're trying to connect to something locally, whether it be your default gateway or something that's on the same network, You'll send out a broadcast message that says, hey, who has this particular IP address? And they will respond with a MAC address. A MAC address is the machine address. If you've ever looked at your machine, or you looked at 802.11 card, or any Wi-Fi card, the Bluetooth, they all have that MAC address that basically is the address assigned to them by the manufacturer. The manufacturers have some preset set of MAC address headers that they use, so you can identify who manufactured a particular device. But here's the problem. MAC addresses are assignable, which means you can't really trust that the person who says they have the MAC address actually has the MAC address. As a matter of fact, for a long time, it was easy to poison ARP tables just by spewing responses before anybody even asked for it. This is called ARP poisoning. So whenever you're on a local network and somebody's trying to get to a machine on the same network, you can just sit there and say, I am that machine, over and over and over again, because whenever there's an ARP request, it will take the first response. It doesn't look for any other responses. So if you answer before the other machine, you're able to take over the IP address of that machine. Now, depending on what you're doing, that's going to be fairly noticeable. One, the flood of ARP requests. Two, if you're trying to do any kind of man-in-the-middle, to be able to do testing, you're going to run into certificate errors, if there's any certificate pinning, anything of that nature. But it's still an old way of doing, a way of taking over an IP address. And it's all because of how the protocols work. Understanding how those protocol works lets you understand how that attack works, and also how you can notice the attack. If all of a sudden you see a spewing of ARP responses, and you're monitoring for those type of things, then you're going to be able to identify, hey, it looks like there's a bad actor on that particular network. All right. So on the same thing with the IP network. Whenever you're doing routing, basically every single packet, you end up rewriting the packet from the source and destination whenever you're at the data link layer, because you have to go from one MAC address to another MAC address. The source and destination IP address don't change, but the source and destination MAC address changes at each hop, because at each hop it says, where's the next place I need to go? And it puts that in the destination, and then the source is wherever it is right now. This all happens very quickly, of course, but it means that you can only really know for sure the MAC addresses on your local network, because as soon as you get off into a router where you're a few hops down, then you're going to not know the exact MAC address that's the end machine has. That's why whenever you're doing something like Nmap, where you're scanning a network, if you scan your local network, you'll see MAC addresses. You'll be able to determine what their MAC addresses are, but if you're scanning the internet, you won't see MAC addresses, because there's no way of determining that. So whenever I'm doing a talk like this, I am doing stream of consciousness. I don't really write a script or anything. If I make a mistake, I apologize. If somebody notices a mistake, feel free and point it out. Like if I say you can not do this in the sense of a MAC address. By default, in a regular situation, you're not going to be able to get the MAC address unless you have the ability to get closer, or some other method of tricking the machine into releasing the information. It doesn't mean it's impossible. It means in a standard situation, you're probably not going to be able to get it. So that's a caveat. All right. If you didn't catch it earlier, I said ICMP is on layer 3. ICMP is the protocol that we use for ping. It's the echo request, echo reply, but it also does other things, like if you're trying to get to a particular network, you may receive an ICMP. It's the, if I remember properly, Internet Connection Messaging Protocol, something of that nature. So basically, if you try to get somewhere and you can't get there, you'll get an ICMP that the host is not found, or an ICMP response that the IP isn't found, or the route not found, or whatever it may be. You'll receive error message via ICMP. So it's not just echo request and echo reply, but it also has other uses. So once we move from layer 3 to layer 4, we start talking about where most people are familiar with networking, which is TCP, UDP. This is the transport layer. This is where you really get into being able to make full connections with remote machines. Right now, what we have so far is the physical connection of how things move from one box to another. Then we have the transport layer, which is how things communicate. Then we have, we have the physical layer, the data link layer, which is how things communicate, the network layer, which allows us to assign IPs and do routing and be able to make it past your local network. And now we get into the transport layer, which is where we get into the communication protocols. TCP and UDP are, of course, the two most popular that we talk about. There are other ones out there, but TCP and UDP will be most of what you deal with. TCP is a communication method that allows for bidirectional communication with protection around it, so that one, you can have a full handshake, which means that the first packet comes across and it's a SYN packet, reaches the machine. The machine will either say SYN-ACK, that yes, I acknowledge the SYN that was sent to me, or it'll send a reset saying no, it's closed. Again, referencing Nmap, if you do a scan of a box and it says something is closed, it's because it received a reset packet. If it says it doesn't know, it's because the packet was just dropped. Properly configured firewalls will probably have it where it's just dropped and you don't know if it's open or closed on a SYN packet. On a TCP port. Unless you're allowed to actually communicate with it. So we send a SYN, it receives a SYN-ACK, and then the client will again send a response of a FIN, which basically just says, okay, that's the finish of the three-way handshake. So with the three-way handshake, it's possible for TCP to be able to verify that there is someone on the other end of a piece of communication. From there are different ways that TCP is allowed to track the communication. If it drops packets, it's able to notify the client or the server that, hey, I received the packets out of order, or I'm missing a packet, because they all have serial numbers and they all have details that allow you to track the communication and verify that you're getting everything you were supposed to get. UDP, on the other hand, is kind of a pass and pray type model, where you send the packet and you hope it gets there. And a lot of protocols, a lot of applications use UDP in the sense of, I'm just going to shove as much data as I can down the pipe. If the person on the other end receives it, great. If they don't, okay. It was often used in streaming protocols early on, meaning 20 years ago. There are still some video streaming protocols that would still use it, but it was also used in things like DNS for domain name resolution, domain name service, to be able to do domain name resolution. So basically you look up a domain and you get an IP address back. The default on that is UDP, though a lot of people have moved to TCP, plus TCP supports larger packets, so if you have more data in there, plus with the TCP model, you're able to verify. One of the things that having UDP is similar to the ARP, where you can poison DNS entries by trying to fill responses for common things. It's gotten a lot better, but there was a lot of problems for a while with DNS and overall how it was verifying the data it was receiving. Once you have the transport layer basically just says, here's the protocol we're going to be using to make that connection, and it will also allow you to specify, like I said, TCP or UDP. Now in that, a lot of times you will also hear that it allows the port. And while you can specify the port, the actual communication is on layer 5, which is where sockets come in. The old way of thinking about this was, you have a phone number into a large building. That's like the IP address is the phone number. And then whenever you call an extension to get a specific person, that's like the port number. Okay. And because it is a two-way communication where you're talking to somebody, that would be like TCP, where sending a fax, for instance, for those of you who remember what faxes are, would be like UDP, where basically you connect and you start sending. Now, we all know that there's actually a handshake that happens at the beginning to verify there's a machine there and all that, but it's not a bidirectional communication. Once it does the handshake, it goes ahead and sends. So that's why the analogy was always flawed, because all analogies are flawed. Um, so whenever we start talking about sockets, we're talking about specifically the ability for two devices to be able to really send data back and forth. That's where we get into that session layer. This is where we start talking about session establishment in TCP over a specific port. Say it's where it makes the initial connection. Now again, this is not the actual data. This is the just the part where it actually makes the connection. So if we think about the physical layer, on the physical layer, we weren't sending data back and forth, but it was how the connection was made. The session is also similar to that, where it's not the actual data that's being sent across, but it's a connection made at that logical level. Once we get into the presentation layer, which is layer 6, then we start talking about things like TLS, whether or not we're going to do encryption. So if we're doing, say, for instance, an HTTP website where we're doing encryption with certificates and everything, first you have to establish the communication with the encryption. So that's technically layer 6. It happens over the socket. And again, these are layered up on top of each other, and it's how it's broken apart. That's why it's good to know. If you're looking for a particular problem with TLS, you can see the entire TLS handshake and certificates being passed and everything else. But once that connection is made, then we get into the application layer where it's actually encrypted and you can't see the data. But that TLS part of it is at the presentation layer. Also at the presentation layer would be MIME encoding or MIME types to be able to say, hey, I'm going to be sending you this kind of data in the sense of a web server or something of that nature. Okay, the last layer is layer 7, the application layer. The application layer is where your data is actually being sent back and forth. So this would be WebSockets, for instance, where once you've made the connection, you've done all the handshaking to verify what type of data is being sent, who's sending it, who's receiving it, the type of communication that's going to happen. Is it going to be encrypted? Is it not going to be encrypted? If it's going to be encrypted, making sure that you can talk to one another because you're using the right version of TLS, plus the right certificates, validate certificates, everything else. Once you've gotten through all that, then you actually start passing data back and forth. This is the application layer. So this is where really the data between client and server happens. All right, so I'm going to stop right there, and I want to say a couple of things real quick. First off, if you want to understand how these protocols work, I highly recommend Wireshark. Wireshark has a great decoding module in it that allows you to see each packet, where you can see it both in the raw form in hex as well as decoding each packet so you can see each one of the layers as you go through it. Matter of fact, I may do a short demonstration of Wireshark as how it relates to this and be able to show you all the different things. Plus, there are a couple of sites that I can try to put it in the description below where you can grab packet captures to be able to say how communications work between two particular applications. One other comment that I wanted to make before I go is people were asking, well, why do you want to make videos? Just write it all down. Well, this stuff has been written down 1,000 times. It's all out there, but people are still having trouble with it, and everybody learns in a different way. I may not be the best presenter. I may not be the perfect, orator. I may not be able to, convey thoughts perfectly every time, but I'm pretty good at being able to describe things the way some people can understand. So I'm doing this to try to help people get a better handle on these concepts. If you want to get into information security, you will do better if you understand how the underlying protocols work, if you understand how these things fit together, and so you can see anomalies easier, you can see what's broken easier. Plus, as I've said several times, If you want to get into information security, go look at the job recs. Search for the terms that you don't know, or search for the terms that you do know. But networking on most system security, where you're a general engineer, information security engineer, or something of that nature, will probably have something about networking. It doesn't mean that you have to understand all the routing protocols or all the protocols for layer 4 or layer 3. You don't have to understand all that, but if you understand how they work, one, you can understand how Nmap works to be able to do security scans, or more specifically, informational scans whenever you're doing footprinting at the beginning of an engagement. You can understand what's the difference between an open port or a filtered port, or an unknown port. Why would it be unknown? Well, if you know how the protocols work, you can explain that, and it also will help you explain to the end user, hey, we found a problem, here's why it's a problem, here's how you can fix it. Whenever you're doing reviews of particular, say, firewalls or network control points, looking at access control lists or ACLs on a router or a switch, or you're looking at access control lists on a firewall or a VPN endpoint. If you're looking at those things and you can see, oh, well, it only blocks at layer 3 and it doesn't add in layer 4, then you can understand why that's bad. Because then all we're blocking is the IP, or we're allowing to the IP. If we're allowing to the IP and we're not doing any filtering at layer 4, that means they can get to every port that's open, and that's probably not what you want, So understanding how all this fits together can be very beneficial to trying to get into information security, but it can also be beneficial trying to get into networking, or even regular system administration. Anytime there's a problem, one of the things, well, used to, it was always the firewall's fault whenever you first started putting them in. I've been doing this for 25 plus years now. And whenever we first started putting in a lot of firewalls in between systems, something would break and it's like, oh, it's the firewall, it's blocking the port we need. Sometimes it was, sometimes it wasn't. But it became a catchphrase of anytime there's a problem of a client and server not working properly, it's the firewall's. And if you understand how all this stuff works together, you can say for sure, yes, it was the firewall's fault, or no, actually the firewall is open, here's where it's open, and it's allowing this traffic, but we are seeing denies over here because you didn't specify the other port you needed that works for this other protocol. So, gonna wrap my rambling up there. If you have any questions, let me know. I will be having other stuff done sometime in the future, hopefully sooner rather than later, and enjoy.